Good morning, students. Mr. Carver here. This is part one of section 5.9. I'm going to break it up into two separate lectures. So part two will be posted in the next class. So here are actually four warm-up problems. Try your hand at them, hit pause, and then hit play. I'm going to work them right now. I should say hit play when you're ready. All right, so number one here, what I want to do again is separate the variables. I'm going to take the y, move it to the left-hand side. I'm going to take the dx, move it to the right-hand side, which is then going to give me this right here. I've got 1 over y dy is equal to x sine of x squared dx. I want to use u substitution on the right-hand side. So this portion right here will be my u. Not only is it innermost, but it's a quadratic, and when I derive it, I will get a linear function. So my u is equal to x squared. Du is equal to 2x dx. Don't need the 2. That comes over here. So the left-hand side is 1 over y dy. That gives me the natural log of y plus c, and that c is going to come to the other side. My right-hand side is going to be 1/2 the integral of the sine of u du. Hope you can read that. That's the sine of u du. When I integrate that, I get the negative cosine. So this will be the natural log of y is equal to negative 1/2 times the cosine of u, which is x squared, plus c. And that is after, of course, this invisible c comes over to the other side and combines with the c, the constant rather, on the right-hand side. All right, so this right here is where I want to solve for c. All right, so I'm going to take the point 0, 1, and I'm going to plug it in there. So that's going to give me the natural log of 1 is equal to negative 1/2 times the cosine of 0 squared plus c. So the natural log of 1 is 0. This is 0. Cosine of 0 is 1, so that means c, when I add negative 1/2 to both sides, I get c is equal to positive 1/2. This is going to go right into here before I solve it for y. All right, so let's get rid of some of this stuff. I got a positive 1/2 for c. Get rid of this. And then this, get rid of this. So then this will be positive 1/2 here. And now I want to solve for y. So I'm going to take this invisible e, and I'm going to move it over to the other side. And I get y is equal to e to the negative 1/2 cosine of x squared plus 1/2. You could leave it like that. You could also raise e to both of those terms in the exponent power. That's negative 1/2 cosine of x squared times e to the 1/2. I'll take either answer there. All right, 2a, that is the arc cosecant of negative 2, which is the same as the arc sine of negative 1/2. So the range there is negative pi over 2 to pi over 2. That looks like it's going to be pi over 6. And it's got to be negative because it's got to be in Q4. There is the answer for 2a. Arctan of negative 1/3 also needs to be in the fourth quadrant. Range of the arctan goes from negative pi over 2 to pi over 2. That also is pi over 6, and it's got to be in the fourth quadrant. Both of those are negative pi over 6. All right, let's jump over to the next page. I'll keep coming back to this so you can see. The half-life of radium-226 is 1,620 years. How long does it take to find a sample, or rather, how many years will it take for a sample to decay to 11% of the original amount? So if you recall, what I want to first do is find c. So I'm going to pick convenient values of c before I use the numbers in the problem, and I'm going to use 2 and 1. I could use 1 and 1/2 as well. I could use anything as long as the eventual amount is 1/2 of my original amount. So I've got e then to the 1,620k. So remember, I'm going to divide by 2, then I'll natural log, then I divide by 1,620. So I get the natural log of 1/2 over 1,620 is equal to k. And those are in your notes from before all this started. So look back if you're wondering how that looks in your calculator. All right, so the natural log of a half divided by 1620, by the way, you want to make sure that the 1/2 is in parentheses, gives you negative 4.7286863 times 10 to the negative fourth. I want to store that into my alpha value of k in my calculator. So again, it's stow alpha k, enter. All right, now I can go about using the numbers in the problem to actually solve the problem. So it looks like 11% of my original quantity. So I'm going to go back. I'm going to start with 100%, and I'm going to go to 11%. You can also think of 100 grams going to 11 grams, and then I've got e to the k times t. T, of course, is what I'm solving for here, and I already, of course, know k. So here we go. Step one, I'm going to divide through by 100. That gives me 0.11 is equal to e to the kt. Then I want to take the e to the other side. So that gives me the natural log of 0.11 is equal to k times t. And of course, lastly, I'm going to divide by k. I get the natural log of 0.11 over k is equal to t. And you can punch it into your graphing calculator exactly like that. Let me do that quickly. All right, that gives me 5,158.77 years. I'll tell you how far I want you to round on the actual test. I think that makes sense. Look, if it's 11%, it's going to be 50% after 1,620 years. There are a few halvings that need to happen before it gets down to actually 11% of the original. So that seems like a reasonable answer. All right, let's get about 5.9 now. Okay, guys, 5.9. These are inverse trig functions and integration. Makes sense that we would spend 2 days. That's integrations. Let's just do integration. 2 days on integration. It is far more complex and uncertain than deriving. There's so many approaches to these problems. And again, just like all the previous integration sections, practice makes perfect. So just hang in there and keep after it. All right, so the first thing we're going to do is start off with this caveat that begins every single integration section, and that is because we're going to be using u substitution throughout. We want to let u be a differentiable function of x. So all these will be written as if u substitution has already happened. We're also going to have the assumption that a is a real number greater than 0. All right, so there are 3 formulas that you need to memorize, and they are as follows. All right, and there are the 3 that you need to quote-unquote memorize. Sounds like we're not going to be back at school. Obviously, the testing environment is going to be such that you will not have to memorize these, since the test will be open book, open note. However, I do believe it is to your advantage to memorize these. So you'll notice that there are only 3 of them. And by the way, I wrote the first 2 in arc sign with the actual letters ARC. The last 2 with secant to the -1, they all mean exactly the same thing. They are interchangeable. I didn't put arc in the last one just to save a little bit of room. Also, you'll notice that there was only 3 of them, and none of the co-function antiderivatives are here. And that is because, for instance, if this first one had a negative right here, what I would do is I would take the -1 and I would move it out to the front, which would then make it the -1 constant times the arc sign of u over a plus c. I suppose you could also have the option of keeping the -1 on the inside, in which case this would be arc cosine. But if you don't want to use any cofunctions, you bring the -1 out front, and this stays the way that it was, and it's just arc sine. So there's really only 3 of them that you need because, again, of the negative constant that you can just pull through the antiderivative. Okay. So let me show you how to use these. All right, we'll start off with a very straightforward one. Okay, so the first example we're going to do is fairly straightforward. I should mention also in section 5.9, there are going to be problems in the textbook that are drawn from previous sections in the textbook. So 5.2, 5.3, 5.4, also from chapter 4. So you should be looking to see whether you can use substitution on these types of problems. A couple of things I notice about this. First, if I look at the denominator here, which is typically what I let u be, I do not have a linear x function in the numerator that would allow me to use u substitution. So that's not a candidate. Also, don't forget, you cannot split denominators. So I can't make that 1/2 plus 1 over 9x squared. That's violating the rules of fractions. So don't do that either. Okay, so I would like you to think of 5/9 integrals as being kind of the method of last resort. And since none of the other previous methods of integration work for this problem, we're going to try to make this look like one of the formulas in section 5.9. And if I look back here, whoops, the only one without an integral is actually number 2 here. Not an integral, excuse me, a square root. 1 over a squared plus u squared. So I'm thinking that this problem right here is going to be an arctan problem, So what I want to do is then, I want to start making this look more like an arctan problem. This is going to be 1 over the square root of 2 squared plus 9x squared is the square of 3x. Okay, now why on earth am I writing it like that? Well, if you remember, the arctan formula is 1 over a squared plus u squared. So what I'm trying to do is identify what a and u are. And what you can see here is that this is exactly what I'm doing. See the innards here. This is a, the innards here is u. Now also, one other thing. U will always be a differentiable function of x. That's the preamble right here. So your x value will always be the u. The a will always be a real number, which again is why this part's a and this part's u. Now, from here on out, it's very similar to u substitution, and you're going to go through and identify exactly what a is. So a, in this case, is the square root of 2. My u is equal to 3x. And then just like I did with regular old u substitution, when I derive that, du gives me 3 dx. And what you'll notice here, again, like all the other problems in chapter 4 and 5, I do not have a 3, so I'm going to bring that 3 over here to the other side. And then what I want to do is take all of this right here, and I want to do a substitution into that formula right there, which is going to give me the integral of 1 over root 2 is a, so that's a squared, plus 3x is u, and that's also being squared, and then I have 1/3, which I'll bring out to the front, du. So now I am ready to go because this integral right here, I have a formula that will tell me how to integrate it, and that's right here. All right, so the answer then is going to be 1/3 times 1 over a. That's 1 over the square root of 2. That is times the arctan of u over a, so that is 3x over the square root of 2 plus c. This is my final answer. So it's 1 over 3 root 2, arctan 3x over root 2 plus c. And again, this formula right here is this formula right there. 1 over a, arctan u over a plus c. All right, now some of these are a little more difficult to see, and let me show you what I'm talking about right now. All right, now if I were to ask you which one this looks like, I think probably the third one. That would be the arcsecant. Looks very similar to this one right here. Get rid of some of this stuff here. Looks very similar to the third one right there. But there's a couple of subtleties here. One is this portion right here is a difference underneath the radical. And if I look at my problem, this is not underneath the radical, nor is it a difference, excuse me. Also, you might be thinking that this could be a difference. It might be the square root of x minus 0. But also, if you recall, that my caveat is that a has to be greater than 0, so it has to be a real number that is larger than 0. It can't be 0. So these two things right here make it not an arcsecant problem. So let me get this out of here, clean this up. So, believe it or not, this is actually going to be an arctangent. Now, let me pause here just for a second and talk about what would happen if I distribute the bottom. So check this out. If I distribute the bottom, I get 1 over x to the 1/2 plus x to the 3/2 dx. Now, it seems like you could just bring that all up to the top, x to the 1/2 plus x to the 3/2, all to the -1 power dx. But as we talked about in class, you cannot distribute this -1 over a sum or a difference. So you can't distribute that and just make each one of those negative, which would be the same, by the way, as splitting this denominator. And we've already talked about the fact that you cannot split denominators. You can split numerators, but not denominators. All right, so that's why U substitution does not work on this problem. So let's get rid of this. And what I'm going to show you now is I'm going to turn this into an arctan problem, or at least attempt to turn it into an arctan problem. So check this out. I'm also going to rearrange it. I'm going to do this first part right here and rewrite it as 1 squared plus the square root of x squared. And then I've got the 1 over the square root of x dx at the end. And you'll see why in just a second I've rearranged this order. Now, if I look at this first part right here, again, the reason I'm writing it that way is to clearly define what a is. A is equal to 1, u is equal to the square root of x, so that I can now do my u substitution. Du is 1 over 2 root x dx. I don't need the 2, but I need everything else. So if I bring that 2 over here, and I get rid of this portion right here is this portion right here. So this integral will, in fact, turn into an arctan problem. So now if I take these three things and I put them into an integral, I get the integral of 1 over a squared plus u squared times 2, that is the worst looking 2 ever, times 2 du. 1 over a squared plus u squared times 2 du. And this portion right here, I have a formula for, so I'm just going to follow it. I've got 2 times 1 over a. That's unnecessary, but we can write it still. Times the arctan of u over a plus c. And by the way, I'm arctanning that quantity right there. So my final answer is 2 times the tan of times arctan square root of x plus c. That's it. So you can see why some of these are they're just difficult to determine the first step or even just how to begin. So that's when practice is going to become your best friend. All right, let's do a couple more. All right, something like this, the integral 1 over x square root x to the 4th minus 4 dx. All right, now this one I think does look like the third one, the arcsecant, because a couple of things are happening here. I've got a difference under here, and as we talked about, this is really close to this, so the order is correct underneath the radical. So it seems to be in line with arcsecant. So let's try to rewrite the innards here and see if we get an arcsecant problem. This is going to be the integral of 1 over, I've got x times the square root of x squared squared minus 2 squared. It's close. It's close. Now, the important part about the arcsecant formula is that this portion right here matches this portion right here. But it doesn't. I've got an x squared on the inside and an x on the outside. So stick with me here just for a little bit. Let's just start working through this and see where we get with this. So my a is equal to 2. My u is x squared. My du is 2x dx. So a couple of things about this. I don't have a 2, so let's just go ahead and move the 2 to the other side. Right. But I also don't have an x and a dx. Now, one thing you'll notice is I need this to be an x squared, and I need an x on the top. So check this out. What if I multiplied by x over x? The top one will go right where I need it on top, and this bottom one will go right where I need it on the bottom. Now, the reason I can multiply by x over x is that is just the same as 1. I'm not changing anything. And this is going to give me this integral. This gives me the integral of 1 over x squared. So this bottom x goes right here. I get the square root of x squared, that's wrong, minus 2 squared. And then on the top, or when I take out my x dx, hang on before I write that. This x on top, whoops, this x on top is going to go right here, and that will give me x dx. Now, I haven't used this u substitution yet, but now I am ready to go. I can do it now. So this gives me the integral of 1 over u times the square root of u minus a, and then my x dx comes out, this right here, and I put in 1/2, I don't like orange, 1/2 du. So now this formula is the formula for the arc secant. So this is going to give me 1/2 times 1 over a times the arc secant of the absolute value of x squared, that's u, over a, plus c. This is my final answer, otherwise known as 1/4 times the arc secant of x squared over 2 plus c. I know the absolute values around the x squared are redundant. I'd always just throw them on there. It's not going to hurt a thing. This then, either one of these two versions are your final answer. All right, just a couple more because I know this is a difficult section. All right, let's try this one. This looks a little bit more like a u substitution problem. In fact, if I let the innards inside of here be my u, so if I let u be 1 minus x squared, my du is negative 2x dx. Now, an x and a dx, I've got a negative 2 here. The problem with this u substitution is this goofy positive 3 here. That really screws things up. I can deal with the 4, I can deal with the negative 2 down here, but the plus 3 is really problematic. So here's what you're going to do in this case. If you're off by a constant in the top, try splitting it. Now, as opposed to the previous ones, we couldn't split it with a sum or a difference in the denominator, but this has a sum in the top. So what I'm going to do is I'm going to take this and actually split it up. I'll pull the 4 out front. That leaves me an x times the square root of 1 minus x squared. And then that's also going to leave me then the plus 3 here. Now remember, the 3 also has to have the common denominator. So I've got 4x over this denominator, plus 3 over this denominator. That's what happens when you split it. Both things on the top need to go over the common denominator. Now check this out. For this portion right here, this u substitution, I can use on this first integral. The second, we're going to have a different approach. But let me finish this out here. So this is negative 1/2 du is equal to dx. And if I do the substitution into this first integral, I'm going to get 4 times the integral of 1 over u to the 1/2 times negative 1/2 du. And we'll get to the second one in just a second. So I'm just working on the first integral for right now. So this is negative 2 on the outside. This is the integral of u to the negative 1/2 du, because I cannot have quotients, so I bring the u to the 1/2 to the top. And let's go ahead and finish out this first one. This is u to the power plus 1 over power plus 1. That's u to the positive 1/2 over 1/2. That gives me negative 4 times my u, which is 1 minus x squared, to the 1/2 power. And this is part of my answer. Now I just need to work on the second integral. The second integral, I can't use u substitution on because I have no x's in the top. So I'm thinking that the second integral will be a 5-9 problem. So what I want to do is start making it look like the arc sine, because this is in the correct order. This is 1 over the square root of 1 squared minus x squared dx. So my a is 1, my u is x, my du is dx. This then turns out to be plus 3, the integral of 1 over the square root of a squared minus u squared du. That's in the formula for number 1 on the formulas that I gave you at the beginning of this video. So this is going to be plus 3 times the arc sine of u over a plus c. And together, those give you the answer for this original integral up here. All right, one more and then I'll let you guys get out of here. All right. Don't forget from chapter 4 and earlier in this chapter, if you've got a top-heavy function, first you have to long divide it. All right, this is what I get when I divide the top by the bottom. I'm putting in missing terms. Don't forget that. They serve as placeholders. So go ahead and pause this, work through it, and see if you match up with me. All right, so this is my remainder, which means if I divide the top by the bottom, this integral becomes that right there. Remember, it's x squared minus 1 plus the remainder over the divisor. All right, so the first two are really easy. It's power plus 1 over power plus 1. This is 1/3 x cubed minus x. The problem is this last one here. U substitution doesn't work. I don't have an x in the top. So what I'm going to do is I'm going to do a 5/9 on this. This is the integral of 1 over 1 squared plus x squared dx. My a is 1. My u is x. My du is dx. This is 1 over a squared plus u squared du, which is formula number 1 on your sheet. So my answer to the third integral there will be plus 1 over 1, or just 1, times the arctan of x over 1, or just x, plus c. So you can tell, even though you've gone through the long division, you still may end up with an integral from 5/9. All right, I think that's probably enough to get you through day 1. Of course, I'm going to answer questions on this later in the week. Just try your hand at it, and again, the assignment will be on my website. Again, hang in there. I know this is not ideal, but I promise we will get you through it. Okay, take care.